Epic. Epic! Epic Stat Tool 1 speedruns of statistics! Brian Stevens versus Chapter 14, Confidence Intervals for the Mean and Standard Signaling Distributions. Hey everybody, we're doing these live today, so welcome to Stat 1 Speedruns. I've got 5 timers open. Let's close down those 5 timers. So here we go. We'll start up the timer and we'll start up the speedrun. So the topics we are covering today for this speedrun are confidence intervals for the mean. When it comes to confidence intervals for the mean, we first need to know the difference between a population and a sample. So we're going to cover these step by step right here. Let's start up by talking the difference between a population and a sample. When we do a population and a sample, we're talking about the difference, and I'm actually going to do something real quick. Usually, got my epic battle right there. Usually I take a picture of these, so I'm going to take a picture and bring this over here into Word so we can talk about it, and I'm not going to highlight this one right here. Little known fact, I actually do the speed runs and do multiple takes. So this is a one-take speed run. Here we go. So now we got over here so we can actually talk about it and draw on it. So let's go ahead and talk about the difference between a population and a sample. Now, when it comes to a population and a sample, for this chapter especially, we're talking about a population being mu, which is the true mean. That's like if you collect data on all UT students and you find out, let's say, the true mean GPA of all UT students is equal to a 3.6, well, then that would be mu. But if you go and talk to a sample, there would be a sample size, and you would get a sample mean. Now, you might get something close to that. We would expect you to get kind of close to it, but you might not get exactly it. We don't know. There's variation within samples, but this is the truth for all students, where this from a sample has a sample size to it. So from 100 students, we observed a sample mean of 3.54. So that is an estimate of the truth. And in many instances, we don't know the truth. We might not know the GPA of all UT students, so we'd have to use a sample to make inferences, inferential statistics, about the truth. When we get down here, have a general understanding of the sampling distribution of the sample mean. Now, this is where the first part of this chapter comes into play. It's quite a long chapter. This is a tough one. Have a general understanding of the sampling distribution of the sample mean. Let's start up a new worksheet right here and talk about this. When we have the sampling distribution of the sample mean, we actually have the idea of a sample mean would be expected, and this is expected right here. This is what the mu stands for. The mean of the sample means, what we expect to see when we take a sample mean, is equal to the true mean. Now let's break down what this means. If UT students have a 3.6 GPA, if you took a sample, you would expect to see 3.6. So just think about this. UT students have a 3.6 GPA. You go out and take a sample of students, you would expect in your sample to see a mean of 3.6. So that is the expected value we expect to see when we take a sample. But we won't always see this value. We will see variation around it. And that's why we have the standard deviation for the distribution of the sample mean. And this is equal to sigma over the square root of n. So as n gets larger, the distribution will get tighter and more normal. These are conditions maybe you're hearing as a review right here, but how does this all look when we put it all together? When we put everything together right here, we get the following. We draw a distribution that looks normal, and at the center of the distribution, we would plot right here, where we have mu y bar, which is just going to be mu, and then we'd go up and down these standard deviations right here. So when we think about this, we would expect, if in our example, students have a GPA of 3.6, we'd expect to see 3.6. If that is the truth. In a sample, like if you go out and talk to 100 students, you'd expect to see 3.6. Now, you might not see that. You're going to see variation around it, because maybe GPAs have a standard deviation, that's what the sigma stands for right there, of 0.5, like a half a point standard deviation. Well, if we take 100 students as our sample, we can now find out the new standard deviation of the distribution, which is going to be equal to 0.5 over 10, which is equal to 0.05. Look at this. It's a much smaller, tighter distribution than the original distribution up here. So now when we take a look at this, We can put our numbers down below. We're just going to put our mean here at the center. So we still expect in a sample, like if we go and sample 100 students, we still expect to see this. And now we're going to go up and down that standard deviation. This is the variation we would expect to see in a sample. So if you took a sample of UT students and found out their GPA, well, it'd be very unusual in a sample of 100 students. This is for 100 students to see a GPA above 3.7. That's 2 standard deviations above the mean right there. And it'd be very unusual in your sample to see a GPA below about 3.5. That's 2 standard deviations right there. So we're talking about what is usual or unusual when we take a sample of students. Like when I take a sample of 100 students, there's the sample size, I would not expect to see in the sample a sample mean that is outside this bounds, given the true mean is 3.6. Very important right here that we know the truth for this distribution. So that's a big understanding right there. We've talked a lot about the sampling distribution, what it is. It's when you know the truth and you go out and take a sample and saying, this is the truth. Here's what I expect to see given this truth right here. Know what y bar and mu represents. We've done a lot of talking about that right there. That is the y bar is the sample mean and mu is the true mean. So a difference between the sample and the truth right there. We've already actually talked a little bit about the central limit theorem, but let's go more in depth on the central limit theorem right here. When it comes to the central limit theorem, there are 2 key things to understand. The central limit theorem. Central limit theorem. The central limit theorem is going to have 1, the distribution will become more normal as the sample size increases. So what we see is that when we have a parent population, and that means like an original population, like let's say the GPA of UT students is skewed to the right. So this is single observations right here where n equals 1. That's just single observations. Like if you talk to one UT student, you're going to see a mean of 3.6, but it's skewed to the right. Now, when you increase the sample size to, let's say, something around 100, or in this instance, 25, because it's not that skewed, the distribution will become more normal. And this is the whole applet that we show in class, where the distribution becomes more normal. It starts to normalize. And what it would be is that every green dot inside of this distribution, like if we talk about one observation over here, one observation is the average of 25. So you would average together those 25 observations because this is the distribution of sample means, where this is sample means right here of size 25, and this right here is single observations. All of these are just y's, they're just observations, which means individual points. So to get the sampling distribution of the sample mean, we have to talk about averaging together multiple observations. And that's maybe where things are confusing, is because this new distribution via the central limit theorem is not single observations like going out and asking one student their GPA. We're going out and averaging together 25 GPAs, and one observation over here in this distribution is the mean of 25 observations, which does have in it its own variation. But the variation, which is the second part of this, the distribution will be tighter, as in, which means it has a smaller standard deviation. So the distribution will be tighter, which means it has a smaller standard deviation. And we saw this just a moment ago. Just a moment ago, we saw via the formula sigma over square root of n. Sigma over square root of n. You might say, why is it sigma? Well, that's because we know the truth right now. In this instance, we know the truth because we're saying, here's the true mean, here's the true standard deviation. This is what we'd expect to see if we went out and took a sample. So this is going to say that it will decrease. Just take a look at where the n is. The n is on the bottom of the equation, which means as sample size decreases, this whole equation will get smaller. So for larger sample sizes, so will be tighter for larger sample sizes. So very important right there, which means the standard deviation is smaller standard deviation. And we see it right there. As n increases, the distribution becomes more normal and also becomes tighter as n increases right here. You can see the tighter right there via the mathematics, and you can see the more normal via kind of the illustration we have right here, that the distribution of the mean for a larger sample size will be more normal. We have right here no assumptions of the central limit theorem. We got some of my favorite stuff right here. The assumptions are going to be condition 1. You're going to hear this a lot today. Random. So the randomization condition means that we randomly select individuals. So we need to randomly select. Any question you say we randomly took UT students. That's what randomization means. 10%, this is a very confusing one. I'm not going to go into great detail on it, but the best thing to memorize right here is less than 10%. Less than 10%. Everyone always wonders, why is it less than? It has to deal with finite mathematics. I'm looking for this research paper I saw a long time ago going over all the mathematical theorems. Really great paper. I can't find it, but it's very technical, and as long as you know less than 10%, you're good. Weird condition. The last condition right here, which is condition number 3, is going to be the large enough sample size condition right here. And what does this mean? Well, if we have a distribution that is normal, n only needs to be 1. If we have a distribution that is skewed, that looks a little heavily skewed right there. If we have a distribution that is skewed, that's n equals 25. And just think about what large enough means. The way I think about large enough is that the sample size is large enough to counteract the skew. So when you have a distribution that is normal, you don't need to take a very large sample size. When you have a distribution that is more skewed, this is like lightly skewed, you need a larger sample size. When you have a distribution that's heavily skewed, you need an even larger sample size. So the more skewed the distribution is, the larger the sample size needs to be. So we have a large enough sample size condition, which means the more skewed the parent population distribution is, the larger the sample size will need to be. If the original distribution is normal, this is normal right here, then it does not need to be large. It can be 1 actually, because everything works, the z-scores all work. So if it's normal, then it's all good. If it's skewed, then 25, and if it's heavily skewed, 100. Those are great notes to take down. 1, 25, 100. Good bookmarks right there. Know the difference between the two distributions. Real world distribution of the sample that might be seen in a histogram, math distribution of a sample statistic as the sample mean. And this is what we've been talking about right here. Let's show that graphic. So we've been going over these two distributions, and we have them right here. So here is the individuals that we can see. So this is what we would see in the world. You go out and take a GPA of a student, you will see one student's GPA. This is literally the question of, hi, what's your GPA? And a student says this, this, this. Now, this distribution over here is the theoretical distribution of what happens if you talk to 25 students infinite amount of times. Every single green dot right here is the average of 25 random individuals, condition 1, from the distribution of individual observations. We call that the parent population sometimes because from it you create all of these sample means. This distribution over here is theoretical because it's what would happen if you infinitely took sample sizes of 25 and average them together to get one observation that is the sample mean for 25 observations. So in this instance, every green dot right here is the average of 25 dots. It took me probably a semester to even be like, okay, what is the sampling distribution of the sample mean? I think that's probably one of the hardest points right here is knowing the difference between the single observations we view versus the theoretical mathematical distribution of the average of all 25. Given the mean and standard deviation of a population, be able to calculate the mean and standard deviation of the sampling distribution. So the mean and the standard deviation of a population. So we have the mean and standard deviation of a population. Very important to know these in notation. The mean and standard deviation of population are mu. About to go off the bottom of the page there. And the standard deviation of population is sigma. And from these, we're going to calculate for a sampling distribution. And we are going to use the formula that mu y bar, which is the mean for the distribution of the sample mean, that's what we're calculating, is equal to mu. That's the easy one. It's just if students have a 3.6 GPA, which would be this right here, then if we take a sample, we would expect to see 3.6. If the average person at UT is 5'9", and we take a sample of students, then we'd expect to see 5'9" as the sample mean. So if the true mean of height is 5'9", then in a sample, I'd expect to see 5'9". That one, hopefully it makes a little bit of sense. It's so like, it's like, wait, that's all it is. If the average student spends $20 a week on snacks, then we'd expect in a sample to see the average person spending $20 a week on snacks. I just want snacks. So now we go and we look at the standard deviation. The standard deviation for the distribution of the sample mean, which is just the variation, is equal to sigma over the square root of n. And we've talked about this a few times right now because all we're doing is decreasing the standard deviation by a factor of the square root of n. So as n gets larger, the standard deviation gets smaller. So good stuff right there. Let's go grab the remaining portion of the review. So we've still got all of this right here. Oh my gosh, we got to speed run it. So here we go. Know the assumptions. Yes. Here we go. So excellent timing right here because we're switching topics a little bit towards confidence intervals. So know the assumptions for the central limit theorem when parameters are unknown. So this is going to switch now to confidence intervals. So let's talk up here and let's just put confidence intervals at the top. So confidence intervals. And when we don't know the true mean and we don't know the true standard deviation, we're working with y bar, which is the sample mean, and we're working with S right here. So randomization, once again, it's always there. Good to see you here, Nick. Ask questions if you got them. So randomization means we randomly select individuals. 10% means we've selected less than 10% of the population. I know that's confusing, but just go with me on it. Due to mathematics, we need to do that for finite populations. And last but not least, we have the nearly normal condition. Now, I like to put large enough n and nearly normal together. Because we can technically use large enough n right here. It's just in other instances we can't. For the first one, we can't use the full extent of the nearly normal. Now that we can actually view it, the distribution, and it's no longer theoretical, we can actually look at the distribution. And if it looks normal, we are good. If it does not look normal, then we need to either look at, let's take a look right here. We'd either need to look at a QQ plot, which should look straight, or we could look at a goodness of fit test, which should have a p-value above 0.05. So let's just put greater than 0.05 right here. So here's your 3 checks right here. And I do want to say this again and again and again. If you're watching this, you can't use bar charts to check this. Definitely take a hint right there. You can't use bar charts to check this because bar charts are quantitative and everything we're dealing with, bar charts are categorical and everything we're dealing with in this chapter is quantitative. We're dealing with quantitative information, so you can't use things like a bar chart, a pie chart. You can use histograms because histograms are going to show you the shape of the distribution. And once again, we can use the large enough n condition through the nearly normal to say, okay, the original distribution is normally shaped. So since we're talking about a confidence interval for a mean of, let's say, 30, we are good. So the nearly normal condition has a little more to it than the large enough n because we can look at the shape and the sample size right here, but we can also look at the normality plot, the QQ plot for normality, or the normal probability plot. And we can also look at the goodness of fit test. I have some videos reviewing those topics a little more in depth, but that is how we can check the nearly normal just to make sure we have a somewhat nearly normal shape to this because we're going to be using things like t-scores and z-scores, especially t-scores in this example right here. Understand the reason for using the t-distribution. So the big reason for using the t-distribution is actually, and a good way to remember this, is S and T sigma z. And I like to say Mr. T is mean if you're doing drugs. So I'm sure he's a super nice guy, but in the 80s, Mr. T, don't do drugs. He's bad. Like he'll not be happy with you right there. So with this, that's the way we memorize it. Mr. T is mean, means. So with this, look at this right here. We got T, we got means. Another way is S and T sigma z. But all we're trying to do here, is put in our heads that when we are doing the mean right here, when we are doing confidence intervals for the mean, we will use the t distribution. Now, you do get these formulas, so you will see these formulas here in a moment, but we're just trying to put into our heads that when we're doing confidence intervals for the mean, we will use the t distribution. This is the one that William Gossett created, and this is a speed run here, so we're not going too much more in depth, but I like to remember S and T, sigma z. So if you have sigma, you'll be using z. If you have S, you're using t, and that's kind of the real basics behind it. Understand the characteristics of the t distribution. So when we think about this t distribution, the t distribution, as I always say, is basically normal. And you'll see in the chat right here, I'm going to put the t distribution calculator. So the t distribution calculator, Mubot should be awake and put that in the chat. So the t distribution is basically normal. What do I mean by that? Well, in instances when we have a t with degrees of freedom equal to, let's say, 60. That's where we put the degrees of freedom. And if you want to make a 95% confidence interval, interestingly enough, the t is actually 2. So the t statistic will be basically 2. I think Mute might not be awake today. And so with the t statistic being basically 2, that's very close to our classic 1.96. So, and as the t gets more degrees of freedom, it becomes more and more and more and more normal. I'm going to go ahead and bring up the t applet right here and put it in the chat. So 2 seconds right here as we bring up the t applet. I have to go here to the main screen, I think. So let's go to the main screen here. Let's put that t applet in the chat. So what you might be noticing in this moment is that this does not look normal. At least the t right down here is not my 1.96 I was talking about. But I did say if we give it about 60 degrees freedom, the t is 2. But if you give it even more degrees of freedom, the t will go even closer to 1.96, which is our classic 95% confidence interval. So when you think about this right here, the t and the z are very similar. It's just that the t is going to have larger difference at lower sample sizes. So the t is basically the z distribution. So that's why we still have the similar conditions of the nearly normal, like we had the large enough n before. So we're doing a more exact calculation brought to us by William Gossett and, of course, Mr. T. So we have right here the t distribution. I might continue the rest of it like this. Understand the margin of error for a confidence interval. When it comes to the margin of error for a confidence interval, you know what? I'm going to go back to my speedrun. Here we go. Oh, sorry, it's loading. Here it goes. Is it not going to do it? Now it'll do it. There we go. When it comes to the margin of error for a confidence interval, the margin of error for a confidence interval is always half the length of the confidence interval. So I like to do some easy questions to make sure we can get this. If you have a confidence interval that goes from 20 to, let's say, 50, what would the margin of error be? It's always half the length of the confidence interval. So we go right here and we do this. There is the margin of error visually. It's plus or minus this amount. See if you can solve this here while we're doing it. So the margin of error is going to be 15. We can solve this by putting in the center of the interval 35 and finding that 35 plus 15 is the upper and 35 minus 15 is the lower. Now, when we do this chapter right here, which is confidence intervals, the margin of error is y bar, and here's the margin of error, plus or minus t with n minus 1 degrees of freedom, s over square root of n. That looks a lot like sigma over square root of n, but we don't know sigma, so s and t, sigma z. The other part has sigma z. Oh, hate it when it does that. And so the margin of error right here is the following, and the margin of error right here is the following. So that is the margin of error right there. It's half the length of the interval. You can always use the formula upper minus lower divided by 2. Half the length of the interval, where you have here the upper and you have here the lower, and you divide by 2. So that'd be 20 divided by 2. Great job, Ella, in the chat right there. Great job. I'm still watching the chat. Don't worry. We'll be starting a new speed run here soon. Woo! Quick speed runs. Calculation of standard error of the sample mean relationship to standard deviation. So the standard error is going to be practicing right here. See if you know what part the standard error is before I highlight it. The standard error is simply going to be this right here. This is the standard error. So it's just the original standard deviation over the square root of n. So that is the standard error. So this is the standard error. That is the standard error of the sample mean, and it gets smaller as n increases. It's much like we were doing before for the previous chapter, hence why it's connected. So that is the standard error, s over square root of n. As n increases, the standard error gets smaller. It's also part of the confidence interval. It's 1/2 of the margin of error. Not half of it literally, but here's the t, which controls the percent confidence, and the standard error is going to be the other portion of the margin of error. I put a star on it because this is starred because it's related to the percent confidence we are using. Find the critical t statistic using the calculator. So we've got one of the calculators up on the screen. Let's head back to that right here. And here we are. So once again, we need to know how to get the degrees of freedom. So if we have a sample size of 100, what are the degrees of freedom for a one sample t? If we have a sample size of 100, what are the degrees of freedom for a one sample t? The degrees of freedom are n minus 1. There's n, and there is minus 1. So always remember one sample t, n minus 1. 1 sample t, n minus 1. So if I took a sample of 258 UT students, 258 minus 1, and there you go. If you notice, this t right here is a lot like the z. I'm also making 95% confidence intervals. It's much easier if we put the 95% inside, and now we could make a 98% confidence interval. It's the same as putting 2% on the outside. So there's a lot of ways to use these applets. This is one of my favorite applets to use right here. And you can see I've made a 98% confidence interval where degrees of freedom are 257. Degrees of freedom are based on the sample size, n minus 1 for a 1 sample t. Calculation of confidence intervals using the formula sheet, we got that. Understand jump output. Ooh, do we have time? Let's go to space. Let's bring up some jump output. We can do this really quickly. Got minutes just before the next one. Let's look at total demand, analyze distribution. We are going to do this. We're going to make this happen. Watch this. You ready? We got literally seconds before I'm starting the next speed run here. Because I think, oh, please let this be the end of this one. Here we go, speed run. So here is the confidence interval right here. The confidence interval is over here. And that is the upper. And that is the lower. So this is the upper. This is the lower. That is the standard error, which is S over square root of n. So you can calculate that right there. That is the standard deviation. That is the sample mean. And that is the sample size. So there is all the notation right there. I'm blocking just a little bit of it. But we have here the upper, the lower. Try for yourself for a moment. See if you can get the margin of error. I'm going to calculate the margin of error for this interval. There's the upper, there's the lower. And it's a 95% confidence interval. It does that by default. There's the percent confidence. And so let's go right here, calculate the margin of error. It's half the length of the interval. So 4971.8621 minus 4632.6851. Half that length. There it is right there. And that is half the length of the interval. That is the margin of error of the interval. So if you were able to get the margin of error right there and understand how to interpret this, I am 95% confident that the true mean total demand for days is contained in the interval. And there's the interval right there, 4,632 to 4,971. Let's see if we have anything else for this one, because we're going to start the next speed run here in a moment. Woo! That's got it. That's the end of the speed run right here, everybody. So let's head out. We'll be back here in a moment with more speed runs. Join the next stream. Bye!